The electric universe theory challenges the traditional view of cosmology by proposing that electricity and electromagnetism, not just gravity, play central roles in shaping the cosmos. According to this theory, the universe is governed by vast, interconnected electric currents that flow through plasma, the most common state of matter in the universe. Plasma, being electrically conductive, reacts strongly to electromagnetic fields, and the interactions between these fields and currents are seen as the driving forces behind many cosmic phenomena. In the electric universe model, stars, galaxies, and even clusters of galaxies are embedded within this vast cosmic electrical circuit. Today, we explore the electric universe through four key triads that describe fundamental components of its framework: stellar magnetic fields, surface fusion, electric fields, and cosmic circuits. By examining the relationships between these concepts, we gain a deeper understanding of how electric universe theorists interpret celestial phenomena through the lens of electric currents, plasma, and electromagnetic forces. Let's begin with the first triad. Triad 1: stellar magnetic fields, plasma, and electric currents. In this first triad, we explore three key concepts at the heart of the electric universe model: stellar magnetic fields, plasma, and electric currents. Together, these elements redefine our understanding of stars, particularly the Sun, by attributing much of their activity and behavior to electric forces. In the conventional model, stars are powered by internal nuclear fusion, and their magnetic fields are explained through internal dynamo effects. However, in the electric universe model, stars are deeply interconnected with their galactic environment through electric currents. These currents flow through plasma, the fourth state of matter, which is highly responsive to electromagnetic fields. By examining this triad, we can see how external electric currents shape the magnetic activity of stars, organize plasma into filaments, and generate the phenomena we observe on their surfaces, such as sunspots and solar cycles. These three components form a dynamic relationship. Electric currents flowing through plasma create and modulate stellar magnetic fields, resulting in observable surface features and cyclical behavior. This view radically shifts the origin of stellar magnetic activity from internal processes to cosmic-scale electrical influences. Let's now explore each of these components in more depth. Magnetic fields, sunspots, and solar cycles. The electric universe theory posits that the Sun's magnetic fields are not generated by an internal dynamo as traditionally believed, but are instead the result of external electric currents, specifically Birkeland currents, interacting with plasma around the star. Sunspots, those dark patches on the Sun's surface, are seen as evidence of electric currents piercing through the plasma. These spots are interpreted as areas where concentrated electric activity is altering the magnetic field. The 11-year solar cycle, which describes the rhythmic increase and decrease in sunspot activity, is linked to fluctuations in cosmic electric inputs, modulating the Sun's magnetic activity. Plasma, magnetohydrodynamics. In the electric universe, plasma plays a pivotal role. Unlike neutral gases, plasma is highly conductive and strongly interacts with electric and magnetic fields. The electric universe theory describes the Sun not as a gravitationally driven thermonuclear reactor, but as a giant plasma discharge. Plasma self-organizes into filaments, like the beautiful arcs of solar prominences, and these filaments are seen as electric currents. These electric interactions, rather than internal thermodynamic processes, control the Sun's behavior. Central to this triad is the concept of Birkeland currents, vast streams of electric current that flow through space, aligning with magnetic fields. These currents are thought to connect stars across galaxies, forming part of a larger cosmic circuit. The Sun, according to EU theory, is not a solitary actor, but a node within this vast electrical network. Changes in these cosmic currents influence the Sun's surface activity, modulating phenomena like solar flares, spots, and even the overall energy output. Stellar magnetic fields, plasma, and electric currents form an intricate relationship in the electric universe model, where external electric currents flowing through interstellar plasma shape the activity of stars. This stands in stark contrast to the mainstream view, which emphasizes internal thermodynamics and magnetohydrodynamics. The EU perspective paints a picture of a cosmos energized by electric currents that interconnect stars and galaxies in a vast web of electromagnetic interactions. The second triad focuses on three interrelated processes central to the electric universe's reinterpretation of stellar activity, surface fusion, magnetic reconnection, and energy release. These concepts provide a new way to understand the intense energy events observed on the surface of stars. In traditional models, nuclear fusion is understood to occur deep within the core of stars, while magnetic reconnection is used to explain events like solar flares. The EU model, however, relocates these processes to the star's surface and attributes them to electric forces. According to this view, fusion occurs not because of gravitational pressure, but because of electric fields generated by cosmic currents. This changes how we interpret solar flares, which in the EU model are caused by sudden electric discharges, not magnetic reconnection. Each of these elements, surface fusion, magnetic reconnection, and energy release, are interconnected through the external electric currents flowing into stars. As these currents fluctuate, they create electric potential differences that lead to fusion and explosive energy discharges. In this triad, we examine how electric fields drive fusion at the surface, how electric discharges cause solar flares, and how the resulting energy is released in massive solar events like coronal mass ejections. According to EU theory, nuclear fusion does not primarily occur in the core of stars but at their surface, driven by electric fields and differences in potential. These fields are created by the cosmic currents interacting with the plasma surrounding the star. Fusion, in this context, is akin to a cosmic-scale lightning discharge. The idea that fusion happens on the surface, triggered by external electric potentials, is a radical departure from the standard model, which holds that immense gravitational pressure at a star's core is the source of fusion energy. Magnetic reconnection, solar flares. EU theorists argue that the mainstream concept of magnetic reconnection, where magnetic field lines break and reconnect, releasing energy, is better explained by electric discharges within plasma. Solar flares, from this perspective, are intense bursts of electric discharge akin to electrical arcs in laboratory plasma experiments. These discharges release energy stored in the plasma and are driven by external cosmic currents rather than internal magnetic reconnection. Energy release, solar flares and CMEs. The intense energy releases seen in solar flares and coronal mass ejections, CMEs, are attributed to electric potential differences between the sun's surface and surrounding cosmic plasma. Just as electric arcs release energy in plasma laboratories, the sun's surface reacts to fluctuations in the cosmic electrical circuit, resulting in these explosive outbursts of energy and matter. In this triad, the electric universe reinterprets key solar phenomena such as fusion and flares as electric discharge events. Fusion is driven by external electric fields at the surface, not by core pressures, and solar flares are seen as plasma discharges rather than magnetic reconnections. This reframing underscores the role of electricity in stellar behavior, emphasizing the importance of external forces over internal processes. Triad 3. Electric fields, plasma currents, and solar wind. The third triad centers on three interconnected aspects of solar and space physics: electric fields, plasma currents, and the solar wind. Each plays a critical role in shaping the interaction between the sun and the surrounding space environment. Traditional models attribute the behavior of the solar wind and the heating of the sun's corona to thermal processes. The electric universe, however, introduces the concept of cosmic electric fields as the primary drivers of these phenomena. Electric fields generated by cosmic currents influence the flow of plasma around the sun. This leads to the formation of plasma currents, which flow outward from the sun in what we observe as the solar wind. In this triad, the elements form a clear chain of influence. External electric fields interact with the sun's plasma, producing currents that flow out into space as the solar wind. This flow of charged particles, in turn, drives space weather phenomena such as auroras and geomagnetic storms. By examining these three interconnected components, we gain insight into how the sun interacts electrically with its cosmic environment, reshaping our understanding of solar wind and space weather dynamics. The perplexing problem of the sun's corona being much hotter than its surface is addressed in the electric universe model by proposing that external electric fields heat the corona. These fields, generated by cosmic currents, accelerate charged particles in the sun's atmosphere, resulting in extreme temperatures far from the star's core. Rather than relying on internal heat transfer, the electric universe theory suggests the corona is a product of electric interactions with the surrounding space plasma. The solar wind, a continuous stream of charged particles from the sun, is viewed as part of a larger plasma current system. In the electric universe model, the sun's plasma wind is driven by electric fields and flows outward as part of the sun's role in a vast cosmic electric circuit. This plasma wind interacts with planetary magnetospheres and contributes to phenomena like auroras and space weather, all seen as products of electric currents, not just thermal expansion. In the electric universe, the solar wind is not simply a byproduct of solar heat, but part of the greater cosmic electrical system. The charged particles within the wind are guided by electric currents extending throughout the heliosphere. These currents interact with planetary magnetic fields, creating auroras and geomagnetic storms, visible reminders of the sun's connection to the cosmic circuit. Electric fields, plasma currents, and solar wind describe the sun's interaction with the surrounding cosmos in terms of electric forces. The heating of the corona and the behavior of the solar wind are understood as products of a cosmic electric circuit, with the sun playing a vital role as a conductor in this vast electrical network. Triad 4: Cosmic circuits, electromagnetic feedback, and stellar stability. The final triad explores the cosmic electrical circuits that power stars, the electromagnetic feedback loops that regulate stellar behavior, and the concept of stellar stability in the electric universe model. These elements combine to offer a fundamentally different perspective on how stars function and remain stable over long periods. In conventional astrophysics, stars are seen as isolated systems that generate energy internally through nuclear fusion, with gravity playing the dominant role in their structure and stability. The electric universe theory, however, sees stars as embedded within vast cosmic circuits, where electric currents provide energy from the outside. These currents create electromagnetic feedback loops that regulate a star's activity, adjusting its energy output and surface phenomena based on variations in the incoming electric current. The relationship between cosmic circuits, feedback loops, and stellar stability is critical in the EU model. The electric currents flowing into a star from the cosmic environment are modulated by electromagnetic feedback loops, which keep the star's energy output stable. This mechanism provides a self-regulating system that explains how stars maintain their energy levels and stability without relying solely on internal processes like gravitational pressure. In electric universe theory, the universe is interconnected by vast cosmic electrical circuits, with stars like the sun functioning as plasma discharges in these circuits. Energy is supplied externally by Birkeland currents that flow through space. This concept implies that stars are not isolated powerhouses but are embedded in a dynamic network that sustains their activity. Stellar behavior, including brightness, sunspot activity, and flares, is modulated by electromagnetic feedback loops. Variations in the current density from cosmic circuits alter the star's activity, creating a self-regulating system. This feedback ensures that stars remain stable and balanced in their energy output over time, shaped by the flow of electric currents in space. Stellar stability, according to the electric universe model, is maintained by external electrical feedback mechanisms. These feedback loops help regulate the energy flowing into the star from the cosmic circuit, preventing erratic or unstable behavior. This notion of stability governed externally contrasts with the conventional view of gravitational equilibrium in stellar models. In the electric universe, stars are part of a vast, self-regulating cosmic electrical circuit. Their energy output, behavior, and stability are influenced by electric currents that flow through space, providing a feedback mechanism that governs stellar activity. This cosmic electrical framework offers a unified explanation for many phenomena that challenge traditional gravitational models. Each of these triads, stellar magnetic fields, plasma and electric currents, surface fusion, magnetic reconnection and energy release, electric fields, plasma currents and solar wind, and cosmic circuits, electromagnetic feedback and stellar stability, illustrates how the electric universe theory recasts our understanding of stars and their interactions with the universe. The overarching theme is that stars are not isolated, self-powered bodies governed solely by gravity and internal fusion. Instead, they are integral parts of a vast cosmic electrical system with electric currents, plasma, and magnetic fields playing dominant roles in regulating their activity. This view challenges traditional astrophysical models by emphasizing external forces and interconnectedness over internal gravitational processes. As we have seen, by exploring these four triads, the electric universe theory offers a framework where electricity and plasma drive stellar phenomena, fostering a deeper understanding of the cosmos and inviting us to reconsider long-held assumptions about the forces that shape it.